Okay, so it's nice to see all of you. Today I'm going to be talking about what's new with a bunch of wires that we've been working on. And I'll start with something that's, I think, obvious to everybody in the room, probably, that heterogeneous integration is, as DJ mentioned, absolutely coming our way. And we need to come up with good solutions to be able to integrate chiplets on a common module. And part of that effort is something that we've been working in the OCP community to define and interfaces that will be very simple, straightforward, and help drive the industry toward converging on chiplet interconnect. So what are the high-level targets for multi-die interconnect? Certainly, we want to get to reasonably high throughput. I've had a number of discussions with folks asking why these proposals don't achieve like absolute best possible throughput. And I think the honest answer is some of the solutions that achieve that drive very complex technology. And we're aiming for something that for most of the future solutions we can envision, we can approach with reasonable, straightforward, simple investment in developing IP. Also, energy efficiency is key. So really the key requirements are keeping it simple, keeping it low power, and allowing for some pretty significant throughput rates up to and beyond a terabit per second. We also want to keep it small. Again, going with the idea of simplicity. The smaller this interface is, the better it can actually shrink as technology evolves. The more simple it is, the less complex analog circuitry there is to port from node to node, which can be a real challenge in getting multiple die to communicate to each other. And we are still very much trying to align on a very simple single supply voltage that's compatible for multiple technologies as well. Oh, and I probably shouldn't leave out, there are probably at least a half a dozen different simple parallel interfaces that different companies are using in the industry today. One of the main goals in the development of what we're calling the bunch of wires is to have relative logical compatibility with these other simple source synchronous systems, things like AIB, like the interface that HBM uses today. So there's a lot of commonality, and we hope to be able to bridge that with this effort. So what's new? We talked about our goals. Now what are we doing about it? I can't help but to thank many people for working together to give our little team on the standards body or in the standards committee input to shape what we're calling a 0.7 draft. Is that what it is? Proposal. Now the DJ's not here, we'll call it a spec. A 0.7 proposal that we want to share with the industry and get feedback. Frankly, we actually had a lot more that was written in the proposal that we actually took out so that we could actually at least set some ground rules that most folks can agree on. I don't want to surf the web in real time because I don't know what else is on my internet browser right now. I don't really want to share my email live with the community. Or you can do that on your laptop. But it really is there. We're quite proud of the effort that again, many people have put in. And we're looking forward to getting feedback from the community on how we can shape the proposal and make it better. In putting out the spec, we actually spent some time to make things more confusing by redefining the modes. What we saw is that we think there's a common base that makes a lot of sense for many people, that we're just going to call that common base bunch of wires today. There also, we believe, will be multiple modes that you can operate kind of above and beyond the bunch of wires. So a bunch of wires, we used to call a bunch of wires base, is a simple unterminated CMOS I/O connection between die. Now we've actually turned what we called bow fast into termination mode for a bunch of wires. So we add termination onto the I/O, and you can obviously run faster and over longer distance because it helps cancel out reflections. We also recognize that I think more modes are possible. So there's a lot of good ideas on how this could be extended. Certainly, we already had one in earlier versions of this discussion where we've talked about bow turbo. Now we can look at those different variants as new modes that we can use to operate in different ways. And we believe, as long as every mode also supports the very basic function, that at least we can guarantee some level of interoperability between multiple chips. We're looking at, again, in this base mode, we also slightly modified the definition and data rates to allow for a higher data rate connection up to 8 gigabits per second with extremely short interconnect, realizing that some really interesting advanced package technology is actually becoming cheaper and more available. And we wanted to make sure that we could support some higher data rates when folks use this advanced technology to have really short interconnect with really low power. Again, we don't require that the super high data rates be supported to be compatible with the basic spec. It's just an extension, realizing that there is room in the channel that we can actually allow folks to bring that data rate up for very short distances. And the reason I asked for Eric to be Mike today, usually Ramin's the guy who gets me out of trouble with the really complicated stuff. Today it'll be Eric. And he'll help explain some of the channel specs that we've added into the proposal. Yeah.
These 8 gigabit per second, is it a source synchronous interface?
Yep.
Something like DeFi?
Yeah, so, and we'll go through the definition, but it's just a very simple 16 data bit, single-ended signal, differential clock, source synchronous interface. The minimum requirement for the spec is 2 gigabits per second data rate. But it can dial up to 5 or even 8 where you've got really short interconnect.
Okay. So there's a spec D5 that's used by the video community.
Yep.
That does like 2.5, 3 gigabit per second today.
Right, and so there's a lot of different specs for simple parallel interfaces, and I think the goal of this is to try to bridge between them. So we can certainly, look at how compatible or incompatible this would be with DeFi. Yep. So the basic definition, again, relatively short interconnect, up to about 10 millimeters at 5 gigabits per second, enabling a new mode 8 gigabits per second for very short interconnect. As Bobby mentioned, less than 1 millimeter is the target today. Also, again, additional modes, termination mode going up to 16 gigabits per second per wire at longer distances up to 50 millimeters, and absolutely leaving room open for future enhancements for new modes. What's it look like? This is just a very simple block diagram of implementing the bunch of wires. I think key interesting areas, we do expect some relatively simple phase alignment that needs to happen for the RX. The TX is going to transmit clock and data together on the same clock edge. We adjust the clock so that we can capture data on the RX. So again, very simple source synchronous interface with selectable termination in the case where somebody would want to be enabling the terminated mode for the interface. So you can turn it on and pay a little extra power to go faster, essentially. We are intentionally agnostic from a point of view of bump pitch for this bunch of wires interface. This we think is actually very critical, because if we specify a specific bump pitch, it limits the number of applications and it limits the data rates that we could achieve in some versions of the bunch of wires implementation. So we don't enforce any specific bump pitch in the proposal, but we are enforcing a signal ordering to address a challenge I think that Wolfgang's going to share with us at the end of the day, which is if you've got multiple bump pitches for multiple die, how do you make them actually integrate together? And one way to make it simpler without defining an exact bump pattern is to just define the bump ordering. So signal ordering defined in the specification, number of data bits per clock bit are defined in the specification. So that there's a path to integrating multiple bump pitches together on the same package technology. We will show some examples. They're all based on a 130 micron bump pitch, and as I mentioned, you can move to coarser or finer bump pitches where you need to. This is a basic implementation of the bump pitch. You can see signal ordering, 16 bits of data, differential clock. We are working on extensions to the proposal that'll define mode bit that helps us get into a calibration mode. And included in this bump pattern is optional FEC bit per 16 data wires. That actually goes with a proposal for what we call the light ECC, where we would use that extra bit to do Reed-Solomon 3432.8 to get a relatively low latency, fairly effective error correction with a bunch of wires interface. And that is optional. Certainly realize that there are some applications that might be streaming data where FEC wouldn't be a requirement. From a test point of view, I will share, and I think I shared in the panel discussion yesterday that this is really just an effort that's starting. We have certainly not defined all the modes that we need to test the bunch of wires interface in the proposal, but we certainly have some interesting ideas on where to start. Certainly leveraging industry standards where we can, IEEE 1149.1, 1500, are specs that are already there. They're something that we could leverage, and they test. They begin to test this interface, bridging from the industry's experience in things like HBM memory integration. Also realize, again, lots of effort needed for defining at-speed tests for system test and for self-test for these modules, and validating that we've gone through calibration for those phase adjust circuitry. I'm going to do just this overview before I hand it over to Eric to take us through the updates in the channel spec. I think we've already covered pretty much all of these specs at a high level throughout the presentation. Key things to point out, again, voltages. We are trying to converge on a standard voltage setting for the IP. We would require that everybody at least be able to operate at 0.9 volts plus or minus 5%. In terms of data rates, 1 to 5 gigabaud for the basic implementation with relatively short trace lengths, up to 8 for the super short reach mode, terminated up to 16. That gives us a 16-bit slice with the capability of moving 80 gigabits per second or up to 256 gigabits per second terminated. And then we can stack those interfaces multiple deep so that we can achieve some pretty significant throughput. 4 rows of the terminated mode would get us close to 1 terabit per second, 800 gigabits per second per millimeter of beachfront, which is pretty significant. I won't go through many more of the details, other than obviously targeting very low latency requirements, corrected bit error rates that are very acceptable with the lightweight FEC that we've recommended. We'll get to bit error rates that are in the orders of thousands of years, so giving a pretty robust interconnect solution for many chiplet-based systems. And simple lightweight ESD, just bridging from standards that we've seen in the industry. On that note, I'm going to ask Eric to come up and just talk through some of the considerations that we've added to the proposal for channel specifications. Thanks, Eric.
Okay. Hi. So the first two charts are just talking about the decision between single-ended and differential, and then we'll have the actual channel spec. So most high-speed interfaces are differential, and so what are the benefits of differential, and then how does that bridge to the bunch of wires spec? So the reason for differential signaling is it's immune to common mode noise coupling, and because the differential will cancel the crosstalk. You have a proper return path. The other half of the differential signal is your return path, and you can have ground shields, and it's a clean return path. And then it doubles the effective amplitude of the signal. So you take those reasons for differential and then think about in-package routing where it's just die-to-die, and do you still really need the differential signaling? So in a multi-layer substrate, you'll have a ground plane, your signals, and another ground plane, and those ground planes are your return path, so you don't really need the benefit of the other half of the pair as your return. The bump pitch will allow relatively large spacing between the signals, which eliminates the benefit, which allows for controlling of the crosstalk. And then with a short connection, die-to-die connection, short traces, you're not going to have a lot of loss, and so you don't need the double amplitude. The single-ended signaling can have a lot of the same benefits, and it sort of eliminates the need for differential. Just sort of schematically, I talked to it a little bit on the previous one, but in package, without ground shields, with differential signaling, you still effectively end up with single-ended crosstalk, and you don't really see the benefit of the differential cancellation. You have one neighbor sees high crosstalk from one pair adjacent to it, and it could be hit on both sides, and you don't see the differential cancellation, so you might as well just go single-ended, half the number of wires, increase the effective total bandwidth. Okay, so now the channel specs. First, for insertion loss, in the what used to be base mode or the unterminated mode, there really is no insertion loss spec, and this is going to be the same for all of the specs. The spec is really for the terminated mode. So the reason that the unterminated doesn't have an insertion loss spec is that you're more dominated by reflections. So that's the reason for the 10 millimeter limit. The round trip delay, keep that a small portion of the unit interval, and that's all that's needed. But in the terminated mode, you can have much longer traces, up to 50 millimeters in the proposed spec, or the So and then the limit of 4 dB at 8 gigahertz. Return loss, again, for the basic bunch of wires, it's expected to be unterminated, and so it doesn't really need any return loss spec. For the terminated mode, similarly, there's a knee in the curve at 8 gigahertz, 16 dB, kind of a typical return loss requirement up to the half the baud rate, and then allowing up to 4 dB at 16 gigahertz. And then finally, the power sum crosstalk. So it's the sum of all aggressors, power sum of all aggressors, and follows this equation and rises to 15 dB at 16 gigahertz. And this is something that's generally achievable in a package substrate routing technology with something like 30 micron dielectric thickness and an air gap between the pairs of 50 microns. So it's not necessarily what's required for functionality probably going up to 15 dB for functionality. 8 gigahertz would be fine, but this is what you would just get with typical routing and 130 micron bump pitch.
So are you assuming a silicon spreader, or you're assuming a FR4 type of?
Something like an FR4, yeah. 3.5 dielectric constant. And then I guess I pass it back to Mark for a summary.
Yeah, thanks, Eric, for doing all the hard work. I appreciate that. So just to summarize, again, we believe the bunch of wires is really very similar to a number of different source synchronous interfaces that are being used in a proprietary fashion. It seems like a good opportunity to converge on a straightforward, easy to implement system that could be built in multiple different technologies, right? So the goal is to allow folks to integrate, 7 nanometer silicon with 12 nanometer silicon with 28 nanometer silicon with RF components if they really want to. And we believe that this spec just rides in a sweet spot for, this proposal rides in a sweet spot for connecting multiple technologies that could be really useful to make these heterogeneous systems. This actually, by my colleague Ramin, who wasn't able to make it here today, has actually enabled a mode to prove this in some 14 nanometer silicon already. So we believe that the proposal as we've defined it is certainly workable, even in the terminated mode. We get to very simple IP complexity and very straightforward ability to port it. This is something that should be done, should be doable with a minimum amount of engineering time per project. And my last chart is my usual. For the three of you who are not already on an ODSA committee, please consider jumping in to help us out. Or if you're a part of an organization that can provide some other assistance, we would love to have you in our team. We are seeking volunteers, starting out with foundries who will support porting this IP into their different process nodes and making space available for folks who want to do experimentation with the IP. So anybody who owns a foundry, please. What's that? Oh, am I hitting my mic? There we go. Anybody who owns a foundry, please jump in and help out. Developing the IP in multiple process nodes is also great. We need folks who will help with that. And ideally, we'd love to have versions of this PHY that are available and free and open so that other folks can bridge from that to develop their own interfaces. And as I mentioned, test is relatively recent in terms of coming into our thought process for the bunch of wires and exactly how we can integrate these systems. So within ODSA, there's a new subgroup forming up. Is that right, Boppy? Still? Yes, a new subgroup forming up for test. So please, if you're a test expertise, if you have test expertise, please come and help us out here. And as I mentioned, we actually had a lot more stuff in the proposal that we actually ripped out to make it more straightforward and understandable for the community. So for items that are not yet covered, including calibration and initialization, we'd love input and we'd love participation from the community so that we can define something that's workable for most. That's all I had. Thanks, everybody. I'm probably way over my time. Okay. Okay, good. If there's any questions, I'd be happy to answer them. Aaron.
Here at the end, you're looking for feedback. Can you describe in your mind what an engagement to get to the end of another implementation looks like? Somebody wanting to work with you on this.
Can I describe our path to done? Okay. I think we'd like to get to something that has a reasonable amount of agreement and consensus. I realize it'll probably be impossible to make something that makes everyone happy, but we'd like to target getting, let's say, compatibility, or everybody looks at it and is equally dissatisfied with it, so that we can move forward and make something that can actually work. No. Bobby's like, okay, we got to release version 0.7 in Amsterdam and be all done in December. That's Bobby's target. And actually, we've had, even without releasing the draft proposal, a lot of folks have heard through workshops or word of mouth and given us some really helpful feedback, which has helped shape the what we're sending out yesterday. And my hope is that as more and more people have access to it and throw darts on it and get in contact with myself, that you can find my contact information on our wiki along with the spec so that we can implement those updates. Most of the time they go through the back channel, they talk to Boppy. He brings it to Ramin and I and beats us with a stick until we come up with something that everybody seems to like. Yep. Okay. If there's no other questions, I will go hand my mic over to the next presenter.